Well, good afternoon, everyone, and welcome to today's live astronomy program. My name is Justin. I'm one of the astronomers here at the Science Museum of Virginia. Happy to be with you again today. If you are joining me for the first time, I want to welcome you to the show. We've done, I think this is actually number 30. The 30th show that we've done over the last year or so. If you haven't seen those previous episodes, we've got them all archived right here on Facebook. You can catch up on YouTube as well, but you don't have to have seen those previous shows to enjoy today's. For those of you that have watched before, welcome back. Always great to have an audience these days. Glad you could join us today. Also want to thank our sponsors for the series, Allianz Partners. Thank you for the support making shows like this possible. Now, before we get started today, a couple of notes. For most of the show, we're going to be using special software, the same kind of software we use here in the Dome at the museum. It's planetarium software called Digistar 7. You can do some pretty cool stuff. So if you're able to, I recommend watching this full screen on a big monitor. If you have it, you'll be able to see some extra details that way in today's show. If you can't do that, that's okay. Glad to have you along for the ride. Let's actually switch over to today's show. Got a few things to share with you, a couple of quick timely news items first. Tomorrow is kind of an important day. It is the equinox. So it is the beginning of spring, officially. We've got a whole science short that we released at the last equinox in the fall about this. But real quickly, what's going on? Well, the axis of the Earth is tilted compared to its orbit. We kind of take a look here at the planet's orientation in space. It defines something we call the celestial coordinate system. There's a celestial pole, celestial equator. It's lined up with Earth's pole and Earth's equator. But the angles here, the red and yellow lines, are not the same as the orientation of Earth's orbit. That blue line there, they are tilted compared to each other. So that means, well, from here on the Earth, if we look out at the sun, should be around here somewhere. There we go. On the equinox tomorrow, it'll cross from the southern half of the celestial sphere to the northern half. If you lived on the equator, it would be directly overhead tomorrow. For those of you here in Richmond, won't be directly overhead, but it does mean that we'll get about 12 hours of daylight. It'll be dark for about 12 hours at night. And kind of cool thing about the equinox is that this is true everywhere on Earth. So we'll have about equal periods of daylight and nighttime here in Richmond, Virginia. Richmond, New Zealand enjoys the same split. So there you go, the equinox tomorrow, first official day of spring. One more quick news item for you. This one is not about tomorrow, it's about yesterday. Yesterday, NASA completed the second green run of the first stage of the SLS Rocket. You may recall, if you watched the shows in January, they did this test in January as well, but that one didn't go quite as planned. It set some limits a little bit too low and shut down early. But yesterday, the 4 engines on the SLS core stage all fired together for the full duration they would need to run to actually get this rocket into space, a little over 8 minutes. It was a pretty impressive test. When this happens, they actually make it rain downwind of the test stand. That's pretty cool. The real purpose of this was to test out all of the systems. It had never operated like this before. So you got to check out the engines, make sure all the plumbing is right, make sure the control computer, the avionics, make sure they're all operating correctly. They also kind of wanted to push the limits of what the core stage can do. So they tested the ability of the engines to steer the rocket in flight. This is called gimbaling. And usually in flight, it would happen fairly small amounts, pretty slow. But in a test like this, you really want to push the limits. So I don't know if they just had a toddler come in and grab onto a joystick and move it around. But I think we're going to see that gimbaling test in just a few more seconds. Here we go. Well, let's switch over. But yeah, there we go. I should imagine someone with an Xbox controller just just going wild. So there we go. Look at those things. It's pretty funny. But it went well. They're able to complete the test, and now in the next month or so, they will refurbish the first stage. You may notice some extra fire up there at the top. That's a feature, not a bug. But there is a little bit of refurbishment that needs to happen, and then they'll ship it down to Florida and get ready for the first launch of the Space Launch System, part of NASA's Artemis program, intended to get the Orion spacecraft and eventually astronauts back to the moon. So there we go, a lot to look forward to. They'll announce a launch date in the coming weeks. But while we wait for that, let's talk more about time. We've got to wait a month for them to ship the rocket stage, a couple weeks to announce a launch date. A few episodes ago, around New Year's, we also talked about short periods of time here on the Earth. We talked about days, months, years. And that's not much. In the last episode, I also talked about some planets, exoplanets discovered around other stars, and how we thought that some of them were pretty old, maybe 11 billion years old. How do astronomers arrive at those large time estimates? Thought we should dive into that just a little bit, but try and go kind of slow. Take it in a couple of stages. So before we get into stars and other planets, let's look at our own planet. How do we figure out when things happened in deep time here on the Earth? How can we look back, not just through days and months and years, but through thousands of years, tens of thousands of years, millions, billions of years? Well, to start, one thing you might be familiar with already is something called carbon-14 dating. That's a form of radiometric dating that relies on a radioactive element. In this case, carbon-14. Carbon-14 forms naturally in the atmosphere. We've got cosmic rays, radiation from space, that enters the atmosphere all the time. It can trigger a couple of different reactions that eventually turns nitrogen atoms into carbon atoms, a specific isotope of carbon, carbon-14. A carbon-14 doesn't last forever. It eventually breaks down, but cosmic rays are always entering the atmosphere, so it's always being produced. So it's always around us. Plants are always absorbing some of this carbon-14 as they undergo photosynthesis. Animals are always absorbing this carbon-14 as they eat plants. So you and I both have some carbon-14 in our bodies right now. But it's not going to be there forever. Plants stop absorbing carbon-14 if they stop photosynthesizing. Animals stop absorbing carbon-14 if they stop eating plants. So then it starts to break down. And if you analyze something that used to be alive, a piece of paper, a scrap of wood, some charcoal, a bone, you can figure out how long it has been since that thing was alive by looking at how much carbon-14 it contains, how much the carbon in that object is that specific isotope, carbon-14. So it works pretty well. It's pretty famous, but it only goes back so far. It doesn't work on everything. You can figure out the age of once living things back to about 50,000 years ago or so if you use that carbon-14 dating. But luckily there are other radioactive elements out there, so there are other ways that we can look back through deep time here on the Earth. Pretty famous radioactive element, uranium, is a good way to do it. It's naturally occurring. It's in rocks here on the Earth, so you can date things that were never alive. Uranium goes through a series of radioactive decays, passing through a few daughter elements along the way, eventually arriving in one particular case here at lead. And so one way that you can find out how old a rock here on Earth is by finding out what the fraction of uranium-238 to lead-208 is. If you know that ratio, you know how old the rock is. And if you can't find those elements, luckily there are many other radioactive isotopes available to you. This is an example of a nuclide chart. This shows you all of the various isotopes, all the forms of all of the elements on the periodic table. Any square on this chart that is not black is a radioactive element, so they'll decay in some characteristic time. So if you choose any two squares on this chart. Theoretically, you could find out how long a rock has been around by comparing how much those elements are present. You probably don't want to choose randomly. There are some better choices than others, but we've got a lot of tools in our toolbox for aging things here on the Earth. And using some of those radioactive elements, we have found some pretty old rocks here on our planet. None of them compare to that age I gave for the planet in the last show, about 11 billion years. But let's see, here on Earth, we've got some rocks in South Africa that are about 3.6 billion years old. There's some rocks in China that are about 3.8 billion years old. In Australia, there's a rock formation that is about 4.4 billion years old. And if they rotate around here, we'll eventually see some in northern Canada that are in the same neighborhood, the upper threes, lower 4 billion year old time range. So it gives us at least an idea of how old our planet is. But most of the rocks on Earth are pretty young. Earth is geologically active. It's got plate tectonics, so the plates and the crust of the planet are moving around. Some are rising up, some are subducting down below others. When rocks sink into the interior of the Earth and they get warmed up and the elements inside get mixed up with everything else that's already in the interior of the Earth. And if those rocks come back to the surface, say through a volcano, those radioactive clocks that we use, those ratios of different elements in the rocks, those get reset. So if you pick up a rock that has recently erupted out of a volcano, check the ratios of some of these elements, you'll find the rock appears very young, even though we think the planet has been around for a pretty long time. So how could we maybe figure out just how long the Earth has been around? Well, luckily, we've got a companion here in the solar system. We've got the moon. We think the history of the Earth and moon are closely tied. Not too long after the Earth formed, we think something big impacted it, and the debris from that impact formed the moon. And luckily for us, in this case, the moon has not been as geologically active as the Earth. Certainly not in recent history. So we can look at the oldest rocks we can find on the moon, and that might tell us how old both the Earth and moon are. If we look back to the Apollo missions, some of the oldest samples they brought back from each of their landing sites, let's see, they're in kind of the same age range as the oldest rocks here on Earth. We've got a little over 3 billion years, a little over 4 billion years. Sorry, those two landed close together, so they're hard to read, but 4.3, 4.5 billion years old. Some of these missions certainly grabbed some younger rocks as well. But as for the oldest samples we can find, looks like we're in the neighborhood of 4.5 billion years. So if the Earth and Moon are both about 4.5 billion years old, does that mean the whole solar system is about 4.5 billion years old? Well, we should probably look around. Are there older rocks out there? It's kind of hard to go around and pick up rocks from every other place in the solar system, but luckily the solar system delivers. From time to time, rocks that have spent long periods of time floating around the sun enter Earth's atmosphere. They land on the surface of the Earth and people find them. We call them meteorites. And then we've got a rock that we can calculate the age of the same way we do with rocks here on Earth or rocks from the moon. And the oldest of these meteorite samples was found in northern Africa about 5 years ago. It's called NWA 11119. 4 ones and a 9. And this rock was found to be a little over 4.5 billion years old, about 4.565 billion years old. A lot of close numbers here. So we seem to be zeroing in on the right answer. This meteorite might represent the oldest rocks, the oldest solid materials to form in the solar system. We think that started happening not too long after the sun itself formed. So the whole solar system, sun included, should be a little over 4.5 billion years old. But all of this relies on having rocks here on Earth for us to analyze. what if you don't have a rock in your hand that you can subject to this kind of test? Well, there are other ways to figure out how old something is, or maybe how old an individual feature is on some other world in the solar system. Let's take a closer look at the moon here as an example. The moon is covered in craters, and they're actually pretty useful for questions like this. Let me show you one crater in particular. It's on the near side of the moon. We can actually see it in the nighttime sky. Here we go. This crater is named Copernicus. It's pretty big, but if we look carefully, there's some little craters nearby, and at least one that hopefully you can see well enough on your screen that is inside Copernicus. So the Copernicus crater I have circled in white with little red dashes, and then there's a smaller crater that maybe you were able to pick it out earlier, but it's circled in blue on the screen now. So let me ask you a question. Which crater formed first? Is it the small one circled in blue, or is it the big one? Is it Copernicus? Which one of these formed first? Well, when something forms a crater on the moon or some other world in the solar system, it requires an impact, a pretty violent event. When the Copernicus crater formed, it would have melted the rocks around it, remade that part of the moon's surface. It spread debris across this region on the moon. If there had been a little crater like that one circled in blue there already, it would have been erased in the impact that formed Copernicus. So that means the big crater, Copernicus, formed first. That blue crater came later. So we already know the relative ages of these craters just by looking at them. And they don't have to be overlapping like this. If we zoom out a little bit, the impact that formed Copernicus left light-colored material spread across a large region on the moon. We call this debris from the impact ejecta. And if we looked carefully over here, there's another large crater. It's called Eratosthenes. And if you look carefully, it may not show up perfectly clear in this image, but the floor of this crater is actually lighter in color, like the ejecta from Copernicus. And this realization, some 60 years ago now, is what really helped start to nail down the history of impacts on the moon. It also helped that the Apollo 12 astronauts picked up some rocks that we're pretty sure are part of that Copernicus ejecta as well. So we know that Copernicus is about 800 million years old. Whatever hit the moon, heated up that region, reset the clocks on the rocks in the Copernicus ejecta. That impact was about 800 million years ago. So the large crater to the northeast there, Eratosthenes, is a little bit older. The small crater that I had circled before is newer than that. That's pretty handy to know. Let's see, looks like I got a question that has come up. Valeria asks, how do they test the rocks to find their age? Well, they do it the same way that I was talking about for rocks here on the Earth. You grab a rock, then you have to send it through some specialized equipment. Often an instrument called a mass spectrometer is used for this. That breaks the rock down into its component atoms, and then you figure out how much of each kind of atom is present. So it destroys the sample usually, but you figure out the age. So it's pretty useful in that respect. And so we can do that with Earth rocks certainly, because here on Earth we pick them up, take them to the lab, test them out. We can do that for some moon rocks because astronauts brought them back, and that helps us when they connect to features like Copernicus crater here. That helps us tie in the answer to other features all over the moon. I mean, we can look somewhere else. Let's see. Oh, here's another good example. There's another bright-colored crater here named Aristarchus. Now this one, I don't know that we have any rocks from Aristarchus, but I can already tell right away how some of these features are related to each other. First, we have some bright-colored ejecta. We think fresh material on the surface of the moon can be light-colored like this. When it's exposed to the surface for a long period of time, there's radiation hitting it all the time, and that tends to weather the rocks. We call it space weathering, oddly enough, and it makes the rocks a little bit darker in color. So this fresh material is light-colored, the older material is dark-colored. We see some light material in the floor of this neighboring crater. It's Herodotus, I believe. So that one's a little bit older. You can also just tell it's a bit older by looking at it. The crater on the right has a nice sharp edge, and the one on the left a little more eroded, so it's been there a little bit longer. Similar case with other craters nearby. Look, that one's almost been erased entirely. A little bit of its rim is still there. Looks like it got flooded with molten rock. That must have been a long time ago. And other features of that crater have kind of been erased. It's got a rounded edge. We know it was a crater. Something hit the moon there, but that must have been a long, long time ago. Maybe closer to the age of the moon itself, that 4.5 billion year clock. So it works pretty well on our moon, works on other moons in the solar system as well. I'm going to jump out to the Jupiter system here. The planet will be in the background. You won't really be able to see it. But I want to show you the 4 largest moons of Jupiter. We've got Io, Europa, Ganymede, and Callisto. And just by looking at them, just by doing something as simple as counting craters on its surface, I can tell you how old these moons are, at least relative to each other. Io didn't see any craters. Most of those features are volcanic, just like fresh volcanic rocks here on Earth. The surface of Io is very young. This is Europa. A few craters there, but the surface is dominated by long cracks in its icy shell. Suggests that shell has been in motion and maybe recycled in some way as well. This is Ganymede. Some more craters. They're probably jumping out at you now, but some long cracks on its surface as well. So maybe some geologic activity in the past. But here on Callisto, it's just craters everywhere. I think I've previously referred to Callisto's surface as the oldest in the solar system, or one of the oldest in the solar system. And we reached that conclusion simply by counting the craters on its surface. It has more craters than any of the other Galilean moons there. We see a higher density of craters on Callisto than any other world in the solar system. So it means that that surface has been exposed to space for longer than any other in the solar system. Pretty cool trick, just by counting craters on various worlds. But we can't see exoplanets in that much detail. So how did I get that 11 billion year old age in the last show? Well, for something like that, we take clues from our own solar system, because all the objects here orbiting the sun seem to be about as old as the sun. So what we really need to know to find the age of other planets and other planetary systems is figure out how old their stars are. So how do we figure that out? Well, it's pretty tough just by looking at a star. So we use another special trick. If you take the light from a star, or any object really, transmit it through, say, a prism or something called a grating, it'll split that light up into its component colors. You get what is called a spectrum. And this is the spectrum of the sun. It's all the light that the sun emits, just split up into the individual colors. It's the familiar visible colors that we know: red, orange, yellow, green, blue. There's a little purple at the very bottom if you look carefully. But it's not a continuous spectrum. There's some dark lines there. Looks a little bit like a barcode. And just like the barcode on an item at the store tells the computer what the item is and how much it costs, this barcode in the spectrum of the sun tells us a lot about our star. The different lines there are made by different elements, the different ingredients that make up the sun. And you can see how different elements behave in a laboratory, see what lines they are responsible for. You can go through very carefully, match up each of these dark lines to a different element on the periodic table that must be responsible for it. So you'll start to pick out features in this spectrum that are caused by hydrogen. You can pick out some features that are caused by sodium, features that are caused by magnesium. I forgot about my camera view. The section, that sea of lines at the bottom, it's caused by elements including hydrogen and iron, calcium, potassium, and a bunch more. So there are many different ingredients that make up the sun, and each one leaves its own individual set of lines, its own fingerprint, if you will, in the sun's spectrum. So you go through the spectrum very carefully, you can figure out which elements are there, you match them up to the periodic table. If you're a fan of chemistry, you know the periodic table is incredibly important. It's something that tells us a lot about the materials that are in the universe around us. It's useful to know which individual elements are present in a star, but well, astronomers, they rarely pass up a chance to make their lives easier. So, astronomers have made a slightly different version of the periodic table. Hydrogen and helium, very important. Let's hang on to those. But sometimes in astronomy, everything else is just a metal. Yeah, carbon, oxygen, nitrogen. Don't really think of those as metals in chemistry, but for astronomers, it works. So we've got hydrogen, helium, and metals. Once you know that, you can do a little bit of quick math. The strength of the lines in the spectrum tell you how much of each element is present. So just by looking at the light the sun puts out, I can tell you that about 74% of it by mass is hydrogen. About 25% of it is helium, and the rest of it, that 1.3%, those are metals. So you might hear an astronomer say that the sun has a metallicity of 0.013. For comparison, human body is about 10% hydrogen, almost no helium, and so the rest is metals. You and I have a metallicity of about 0.9. That's not really fair to compare the human body to a star, but we can compare different stars to one another. And we see that, well, stars seem to fall into a couple of different groups just based on the amount of metals that they have. Astronomers break them up into different populations of stars, and they're related by age. So you can think of them like generations of people. You may not be exactly the same age as your siblings, but you're all part of the same generation. So we've got population 1 stars. They aren't all exactly the same age, but they're in a large ballpark, and they've all got roughly the same metallicity, at least 1/10 of the sun's levels of those other elements. Population 2 stars, a little bit older, and they've got a little fewer of those other elements, so a lower metallicity in those stars, so a different generation. I don't know, population 1 stars are the universe's millennials, population 2, that's Gen X, and then population 3, they formed very early on, a burst of star formation after the universe got started. I don't know, the universe's baby boomers, and they, we think, are almost metal free. We haven't actually observed any population 3 stars, but we think they should be out there. So that gives us a rough breakdown of how old each star is, but it just gives us a big range. It's not going to get us to exactly the age of a star. For that, we need to look a little bit closer at the spectrum, and let me compare a couple of individual stars. Not only do the different elements make different lines in the spectrum there, the temperature of the star will also make some of the lines easier or more difficult to see. Like say we've got a slightly hotter star. Procyon is a good example. Here is the spectrum of Procyon. Looks pretty similar, but if we fade back to the sun, I can see a few more lines in the sun's spectrum. If we go to a cooler star, Arcturus is a decent example. I think I see even more lines in that one, especially down at the bottom. That's pretty interesting. So just by looking at the spectrum of a star, we can pretty quickly tell what temperature the star is. If you've been to a lot of shows here, you may have heard me say before that the color of a star tells us its temperature. The spectrum is really the same thing. The spectrum is just all of the colors that a star emits, so they're very related concepts. But here we're looking specifically at these different dark lines in the spectrum. So the pattern of lines will tell us the temperature of a star as well. If you aren't seeing the differences as we cycle through them here, let me put them all on the screen for you, and then you might be able to see the differences. So on the left, that was the hotter star. Middle is the sun, a little bit cooler. The one on the right, even cooler still, and hopefully you can see that changing pattern. Now, astronomers notice that pattern too. They realize that, again, we can break things up into different groups. Instead of coming up with complicated names, astronomers simply assigned letters to these groups. So a star like the sun is a G-type star. There are F stars, there are K stars, and there are a few other groups as well. Through an accident, they don't end up being in alphabetical order when we break them up by temperature. But we can take the pattern of lines and the temperatures of the stars. So those letters down at the bottom of this chart represents. You can see F, G, and K there again. So the sun would be a G star. The hotter stars are over on the left, the O stars. They're even cooler stars, the M stars there. And we're going to compare it here with the brightness of the star. In astronomy, we call it luminosity. So we've got bright stars at the top, dimmer stars at the bottom. This is called a Hertzsprung-Russell diagram, or HR diagram for short, and every star has its own unique place on a diagram like this. Most will be found in that line that goes from the top left to the bottom right. It's called the main sequence. Some big giant stars will be in the top right. Some small former stars like white dwarfs will be in the bottom left. Now one kind of cool thing is that the stars actually move across this chart as they age. So this is where we finally get back to the topic of ages. If you know where a star is on the HR diagram, you might be able to figure out how old it is. In the case of the sun, pretty quickly after it formed, it settled onto the main sequence, and that's where it has been for most of the last 4.5 billion years. The only difficulty is it's going to be on the main sequence for the next 4.5, 5 billion years or so. But once it begins to move off the main sequence, we'll know it's roughly 10 billion years old. It'll swell into a red giant star. It will eventually blow off its outer layers, form a planetary nebula. It'll reappear on the HR diagram as a white dwarf in the bottom left. So this is kind of useful. A little bit tough to measure the age of an individual star this way, but say you have a cluster of stars. Then, oh look, there's one. You can measure the brightness and the temperature of every star in that cluster. You could put that whole cluster onto the HR diagram. It might look something kind of like this. If the cluster is pretty young, almost all of the stars are still going to be on that straight line that cuts diagonally across the diagram. They'll all still be on the main sequence. In this case, a few of the stars at the top left have started to veer off into that top right corner. Now, stars follow a few simple rules, and one of them is that the bigger, hotter stars burn through their fuel faster. So it'll always be those stars in the top left that start moving to the right earlier. So by seeing which stars are just about to move off the main sequence but haven't done it yet, we know how old that whole cluster must be, because they all would have formed at about the same time from the same cloud of dust and gas. If the cluster were a little bit older, measure the temperature, measure the brightness, put them on the HR diagram. Even some medium-sized and small stars have started to turn off of that main sequence, starting to show their age a little bit. And that'll show you the age of the whole cluster. So that's a really useful technique. That's how we find the age of a lot of stars. Now, sometimes, even though stars are born together in a family, in a cluster, they spread out over time. So it can be a little bit tough to get the age of individual stars this way. But if you carefully measure, say, a star's distance from us and its motion through the galaxy, you might be able to link it back to some of its other siblings, even if they've spread out over time. And then you can estimate the age of individual stars. In the case of at least one star, the one you're seeing here, HD 140283, astronomers arrived at an estimate of about 14.4 billion years. This may well be the oldest star in the Milky Way galaxy. So that could actually help us figure out the age of the galaxy. Interesting. But what if we have an even larger collection of stars? What if we want to know the age of some other distant galaxy? Well, for that, we're going to need one additional technique. Let's get out away from the Milky Way, see some of the other galaxies here. Speed up just a little bit so we can get out there. There are many galaxies spread across the universe, and for most of them, they're too far away for us to individually zoom in on, say, a cluster of stars or especially individual stars and see how old those individual pieces are to put an age on the entire galaxy. Luckily, again, stars follow a few basic rules, and in large numbers, stars, their group behavior can point us towards the age of the entire system. So let's say we pick one galaxy. For this example, we'll use one that was the subject of an actual study a couple of years ago. It's M87, also the host of the supermassive black hole Povegui that was imaged a couple of years ago, but that's another show. Astronomers took images of M87 repeatedly using the same equipment, and they drilled down, they zoomed into the individual pixels in this image, and they found each individual pixel changed in brightness, and each individual pixel had its own specific pattern. So kind of like in a spectrum of a star, if you look down at the individual colors, some will be bright, some will be dark. That can help you find out a lot about the star. Finding out the changes in brightness at the pixel level for an individual galaxy can tell us about the whole galaxy. They called this effect pixel shimmer. It's not just an Instagram filter. For M87, it showed us that the galaxy could be about 11 billion years old. We figured that out just by taking a bunch of pictures of it. We didn't have to study the individual stars. We just know that, well, on average, if you have a lot of young stars, they'll actually vary more than they do in M87, so it makes M87 look like kind of an old galaxy. So we got a big number here, about 11 billion years old, and about 14 billion years old for the oldest star in the Milky Way. Can those kind of numbers tell us how old the entire universe is? Well, sure. If we never find a star or galaxy that is more than 11 or 14 or 20 billion years, we know that must be the age of the universe, or at least the universe is no older than that. But luckily, the universe itself can tell us how old it is. We don't find this number by looking at individual stars or galaxies. For this, we have to look all the way back to the oldest light in the universe. The first light to travel through the universe after the Big Bang is now visible as what is called the cosmic microwave background, or cosmic background radiation. And if you look at this light and you break it down into its component parts, kind of like a star's spectrum, gives us so much information and encodes the temperature and age of the star. The light that first traveled through the universe after the Big Bang tells us the mixture of ingredients that were present in those early days. In this case, we're not talking about hydrogen, helium, and metals. We're talking about the different kinds of matter and energy. The elements that you and I are made out of, baryonic matter, dark matter, dark energy. And once you know that breakdown, then you can get the age of the universe, and that turns out to be about 13.8 billion years. Now you might be noticing a small problem here. How is there a star in our galaxy that's a little older than the universe itself? Well, there's a lot of uncertainty in these measurements, and the error bars, the uncertainty in that age of the star is about 0.8. So it could be 13.4 billion years old. That works perfectly with the age of the universe. Even though there's some uncertainty, we see that different techniques point us in the same age ranges for a diverse set of objects in the universe. We can be pretty sure that the whole universe is about 13.8 billion years old. You know, the ages of galaxies can be measured on that same scale. We know that multiple generations of stars have been born in the universe since it started, so we know that not all stars are going to be quite as old as the universe itself. We know that stars are still forming today, and so there are some pretty young objects out there as well. So just from a few simple techniques, measuring either elements in a rock, solid objects, counting craters, breaking light up into its component parts, we can learn an awful lot about the universe around us, including how old it is. And I guess since we're at the edge of the universe, that should pretty much wrap up today's show. Now, if you have any questions about today's show or ideas for future shows, things you'd really love to see us explore, please leave those in the comments down below. Be happy to revisit some of your favorite topics in future episodes. I'll be back in a couple of weeks. It'll be Friday, April 2nd. I corrected the text on the screen for you this time. So it will be again 3:30 p.m. Eastern Time, Friday, April 2nd. That'll be our next show, bringing you up to date on all kinds of things happening around the universe. We've got the OSIRIS-REx spacecraft revisiting its asteroid target in early April. The Ingenuity helicopter on Mars may be flying in the first week of April. I know they have picked the flight zone for it. So we'll have some exciting updates for you. I hope you can join me again for our next show right back here on Facebook from the Science Museum of Virginia. Thanks for watching today. Hope you enjoyed the show. I hope you have a great equinox together. Happy spring. Stay safe out there. I will see you next time.